Okay, so let us continue from where we left last time. So we were discussing about linear dependence and independence, and then so if two non-trivial vectors x1 and x2 both lie on the same line, then the span will be the same line. So this is something we have seen also in the last class. So if there is a vector and there is another vector, this also lies on the same line. So this is x1 and this is x2. Okay, so if I do a span of this x1 and x2, then I will remain on the same line. Okay, because a span of this will be c1 x1 plus c2 x2. But the fact that x1 and x2 are on the same line, then I can write x1 is equal to c times x2. Okay, so I can substitute that here. Okay, so this becomes c times x2 plus c2 x2. So this becomes c plus c2 x2. So this is still the along the same direction, right? So anything that I compute, any span that I compute is still on the same line. It is still a scalar multiple of the vectors on the line itself. On the other hand, if they don't lie on the same line, so if they don't lie on the same line, then span of x1, x2 consists of the entire plane. Okay, so this is something we also saw in the last class. So if the vector is like this, so they are not on the same line. Okay, so if they are not on the same line, then the span will cover the entire plane. So it will be everything, any vector you give in the plane, it can be generated using this. So a span of these two vectors will generate any arbitrary vector. Okay, if the two vectors are not on the same line. So the span of two vectors may be a plane, or it could be something simpler. So it could be either a line or even just zero. Okay, in the case that x1 and x2 are both zero, then the span of zero is just a zero vector. Similarly, if three non-trivial vectors x1, x2, x3 all lie on the same line, then span of these three vectors will be just the same line itself. Okay, so this is the case where all three vectors are on the same line, so the span will be some vectors on the same line itself. Okay.
Hello, sir.
If they don't lie on the same line, but lie on the same plane, then the span will be just that plane. Okay, so if we have a plane and they so these vectors all lie on the same plane, then the span will be the same plane itself. So if they don't all lie on the same plane, then the span is going to look like the space itself. So if I have so span, so these guys and this guy and this guy, so they are, none of them are on the not all three are on the same plane. Okay, so then the span of this will make it R3. Okay, so it will be equivalent to, it will fill the whole of R3. So how do we put these ideas in maths lingo, and how can we be precise? A set of vectors v1 to vk in Rm is linearly independent if and only if the solution to the equation is the solution xi equals to 0 for I greater than equal to 1 less than equal to k. So what this is trying to say is to check whether the vectors are linearly independent or not. You form an equation like this and equate it to 0. And if it turns out that x1, x2, all these are 0 for all I 1 to k, then the vectors must be linearly independent. Okay, so because if not, then you can if one of the one component of the xi is not equal to 0, if that is the case, then we can always write one of the vector as a linear combination of the other. So for example, if let us say x, the component, let us say I denote by j. So for the ith vector, the jth component of the ith vector is, let us say, is not equal to 0. Okay, so this is the converse thing that we are writing now. So this would mean that xij and then vi, okay, is equal to the remaining vectors, okay, which is minus x1 v1 minus x2 v2 and so on minus xk k vk, okay, dot dot dot. So here since xij is not equal to 0, I can divide by that. So vi I can write as a linear combination of these guys. So minus x1 by xji v1 and so on. Okay, so I could write one ith vector as a linear combination of the other. So then hence they are not dependent. So this is what it is trying to say here is for a set of vectors to be linearly independent, you form a linear combination of these with xi being the variable. And if it turns out that xi is forced to be 0, then they are linearly independent. Okay, you could have also written this in the matrix form like I explained in the last class. So it's v1, v2, vk, and then you have x1, xk, and this is equal to 0. Okay, so this is the matrix equation. So if the solution to the, so let us say this is like 0. Okay, so if the solution to the matrix equation is like x is forced to be 0, then the vectors are linearly independent. So if the set is linearly independent, then the span is as big as possible. Okay, so it's as big as possible. Otherwise, they are supposed to be dependent. If the set is linearly dependent, then the span is thinner than it has to be. Okay, so you can always eliminate a vector if the set is linearly dependent. Then that's what it means. There is always a vector v1, v2, let us say vk, and if this set is linearly dependent, then it is always possible that one vector can be removed from the span, and still the one vector could be removed, and still the span will be the same. Span will be the same. Okay, so that's what it's trying to say here. Okay, so this is what he's trying to say. We could even throw away some and still don't change the span. So in this picture, if you see, then these three vectors are linearly dependent. They are linearly dependent because there are three vectors and they all lie in one plane. Okay, so this is the case where it's dependent. If they were independent, they would have spanned the whole of the R3, but that is not what they are doing. They are only spanning a plane. So in this case, you will see that v1, v2, v3 are linearly independent because these two are spanning the plane, but the other vector that you have, it's not in the plane. So this will make sure that the whole space will be filled. Okay, because this is outside the plane. So now you can generate any vector. These guys will make sure that the whole of this plane vectors is generated, and then the one that is not in there can allow you to generate other vectors as well. So example 1, if even a single vi is equal to 0, then v1 to vk will be linearly dependent. Okay, so that is like a trivial statement. So what it's trying to say is that if you have a collection of vector, and if you have one of the vector in your collection to be 0 vector, then whole of that becomes linearly dependent. Okay, so whole of that becomes linearly dependent. So and yeah, so why it would be the case, like why it could be linearly dependent, right? So one possibility is to prove this from the definition itself. So the definition says is like a set of vectors. This is not linearly independent. Okay, so the set v1 vk is not linearly independent or it is linearly dependent if there exists x1, x2, xk, not all zero,
Hello,
not all
sir.
zero, such
Hello.
that you can
Hello, sir.
write it
Can you hear
as
me?
x1 v1 plus x2 v2
Hello, sir.
plus
Can you hear me?
xk
Sir,
vk,
today is
and then
holiday, right?
goes to 0. So this is when it will be dependent,
Hello,
when
sir.
I can produce one of the xi to be, at least one of the xi to be non-zero, and such that this linear
Isn't
combination will be
today
zero,
holiday?
right? So what I'm given is that one of the vector itself is zero. Okay, so let us say some of the vector, some vi vector is zero, right? So here I can write that. So let us say that xi goes with vi, and then you have this. So what I'm given is that vi is equal to 0. So if vi is equal to 0, then I have a liberty to choose xi to be non-zero. Okay, so choose xi to be equal to c, which is not equal to 0. So this implies that, and others you can make it 0, and that doesn't matter, right? So you choose others to be 0, xi's to be 0. Okay, I mean xj to be 0, and j not equal to I. Okay, for all j. So if you do that, then you have 0 v1 plus 0 v2 plus dot 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 plus c times vi plus dot 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 plus 0 times vk. Now whole thing is 0 because here vi is 0. So you have produced a combination of the xi scalars such that not all are 0 and still the linear combination is 0. So this proves that any vector collection, if you have a 0 vector, it is supposed to be going to be dependent. Okay, so this is what is proved here. If even a single vi is a multiple of different vj, then vi vk is linearly dependent. Okay, so you can again establish this fact that if any of the vector vi is some multiple of vj, then the whole set is going to be dependent. Okay, so a pair of vectors u and v is linearly dependent if and only if at least one of the vector is a multiple of the other. In the pair case, when you have only two vector, so if they are supposed to be dependent, then alpha u plus beta v is 0, and so they are linearly dependent, then one must be a scalar multiple of the other, right? So in this case they are linearly dependent, then I alpha or beta is not equal to 0, at least one of that. So assume alpha not equal to 0. If alpha is not equal to 0, right, then since alpha is not equal to 0, you can divide by alpha. So this is minus beta by alpha v. So one can be written as a scalar. This is a scalar multiple of the other. Okay. So more generally, if any subset of these is linearly dependent, then the whole set will be linearly dependent. Okay, so you just have to find any subset of this being linearly dependent. Okay, so I will not do all the details. Okay, so how to check whether a set of vectors is linearly dependent? Well, you form, as I said, you form the matrix equation like this, where it's the same argument as before. So this is a2 and an, and you form put these scalars variables here. And if the solution to this is the fact that x equals to 0, solution to this is forces you to have x equals to 0, then it's linearly independent. If not,
Hello,
then it's
sir.
dependent.
Hello, sir.
A set of more than m vectors in Rm will be linearly dependent. Okay, so that's also like a fact now, because let us say m is 2 here. So m is 2. So let us say I have so more than m vector, right? So in R2, if I'm given more than 2 vector, which is m here, right? If I'm given more than 2 vector, then they are supposed to be linearly dependent only, because in R2, like these guys can generate any vector. Okay, so this vector can be generated using this vector. Okay, so hence more than any two vector are surely going to be dependent, because the third one can be generated using the two only. So in general case, in Rm, if you put more than m plus more than m vectors, then the set containing those more than m vectors are supposed to be dependent. Okay, so so the question here is this set of vectors linearly dependent or linearly independent? Okay, so this is the question here. Like, what do you like think? So how can you say whether this is dependent or independent? So these are the choices you have. Okay, and then you have to identify whether this is dependent or independent. Okay. So as I said, one possibility is to write this as a matrix equation. So 2, 3, 4 and 3, 4, 5. And then I write this as matrix equations x1, x2. Okay, and then the right hand side I put as 0. Okay, and then if the solution to this is surely 0, then the matrix is then these vectors are linearly independent. Okay, otherwise it's dependent. Okay, so you're supposed to solve this system now. Okay. So yeah, so this is the answers are already given here. Like, since this is a like another argument was like this is a two pair, so the pair of vectors are dependent only when one is a multiple of the other, and in this case clearly one vector is not a multiple of the other. So is this set of vectors linearly dependent or independent? Again, okay, you need to find out. But in this case, if you observe that a subset is dependent, for instance, if you consider a subset of this, which consists of these two, so we invoke the previous argument, then this is indeed a 2 times of this. Okay, so since the subset is dependent, the bigger set is also going to be dependent. Okay, so hence the answer is that this is not linearly independent, or this is linearly dependent. Similarly, is this the set? Is this set of vectors linearly dependent or independent? Okay, so in this case, we can look into the subset argument. Like, is this multiple of this? Not really. Is this multiple of this? Not really. So that argument, that subset is dependent, but still it could be dependent. Okay, so another way it could be dependent is like, can I get let us say this vector by a linear combination of these two vector. Okay, so these are the questions we may ask, like, can we generate one of the vector as a linear combination of the other vector, right? So when in doubt, like, then one has to go and solve the linear system, like 1 1 0 1 3 2 4 9 5, and then x1 x2 x3, and then in this 0 0 0. Okay, right hand side is always 0 when you're doing this check. So if you solve this and if it turns out that this is 0, then it's independent. Okay, so I'm going to skip this now. You know how to do this, and this is like now a definition. Okay, so or a theorem. So a set of vectors is linearly dependent if and only if at least one of the vector is in the span of the other. Okay, so if I can write one of the vector as a linear combination of the remaining, then the set is linearly dependent. So that is something we already know. Okay, so I'm going to skip this. So in pictures, how the vectors are dependent or independent. For as I told you before, this is a dependent case. This is an independent case. Okay, so that's all for linear dependence and independence. And now I go to linear transform. Okay, linear transform. So linear transformation is nothing but just a function. But so let us quickly see a function definition. So a function f from a set x to set y is a rule that assigns to each element in x an element in y. So this is just the definition of a function, and it is denoted by f from x to y. And the element of y that is assigned to x is written as f of x. X is called the domain here. So this x is called the domain, and this is called the image. I mean, not image, but the range of f. Okay. So actually, it's called codomain. Okay. Sorry, I should not mix too many things. So this is called codomain, and it's not necessary that f of x is whole of y. Okay. So f of x may not be whole of y, may not. So codomain may not be range. So f of x, so if you do f of the whole set x, so this is the set of all f of x such that x is in the domain. Okay, so you collect all those f of x, then it is called the range of f. Okay, and as I said, f of this set x may not be the whole set y. Okay, so this y has a term called codomain. So let x be the set of students in the room, y be the set of names in the universe. Then there is a naming of the function which assigns to each person in the room his or her name. The functions we are interested in is linear transformations. So what is a linear transformation? It's a function from Rn to Rn. So you see these things are now generalized. So n and m can be large numbers. And it's a call, so it's a function with additional properties that for any vectors u and v in Rn, t of u plus v is tu plus tv. And another thing it has to satisfy is that for any vector in Rn and any scalar in a real number, t of cu is c times t of u. So you must remember these two things to identify whether a function is a linear transformation or not. Let us see some examples. So let us consider this function f from R1 to R1 be defined by tx is equal to 5x. Now the question is this a linear transform? Okay, so is this a linear transform? So you have to check these two properties, right? So you have to choose any arbitrary vector u and v. So let us say I choose any arbitrary vector u and v. So in this case, we are working with R1. So now I have to check whether this identity holds. So I will do t of u plus v. Okay, so t of u plus v, the function is defined as 5 of x. So it's 5 of u plus v. Okay, so this is this, and now I will check the right hand side. So this is the left hand side. Now right hand side is t of u plus t of v. So t of u plus t of v. So what is this? Right, so t of u is 5 of u plus t of v is 5 of v. Okay, but I can take 5 common, so this is 5 of u plus v. Okay, and indeed this is equal to this, LHS is equal to RHS. So this condition is satisfied. Now I choose any vector u and c. Okay, so I do t of cu. So t of cu is 5 of cu. Okay, I can take 5 cu. Okay, so this is like I can write this as c times, because it's a scalar, which is c times t of u. So this is also satisfied. So hence it's a linear transform. Now another question is, can you verify that this is a linear transformation or not? Okay, so whether this is a linear transformation or not. So you must recall, so what you are supposed to do is t of u plus v must be t of u plus t of v. So that's the first point that you have to do. And the second point is t of cu for any u is C times T of U. So whether this will be satisfied for all U and V and all C, that's what you have to check here, right? So is this thing. So if you focus on just this guy, you can then let us say I want to choose C is 2. So T of 2 times U, okay, U is some arbitrary vector. Since this is R1, U also becomes a scalar actually. So T of U is 2U squared, which is 4U squared. Okay. And if we calculate this, C of TU, so C of TU is C times U squared. Okay. So this C was 2 for us, 2U squared. But these are not equal. Okay. So since this condition is violated, this is not a linear transform. Okay, same question. Let us say here, is this a linear transform x plus 5? And you will verify that this is also not a linear transform. I leave this as an exercise. You have to satisfy those conditions. Okay. A linear transform always takes vectors, two vectors. These are the things you have to remember. Most functions are actually not linear transforms. So there are a lot more nonlinear transform than linear transform. For example, let us say if you see the cos function, then cos of x plus y is not equal to cos x plus y. If cos was a linear transform, it must have been equal, but we know that this is not the case. For any linear transformation, t of 0 should be 0. Okay, t of 0 must always be 0. Now this is an easy thing to prove from our second property of the linear transform. So which says that t of cu is c of tu. And explicitly, so here what we are trying to say is like for a 0 vector, so 0 vector, a linear transform always moves 0 vector to 0 vector and nothing else. Okay, so that's what it's trying to say. So, but I can prove this because t of 0, I can write this as t of 0 times 0. So I choose C to be like this, 0 again, and this doesn't violate this, it's still 0. And due to linear transformation property, the scalar comes out. So this will be 0 t times 0. Now 0 times any vector, it must be 0 vector. Okay, so this is what it says, t of 0 is always mapped to 0 due to the linear transformation property. Actually, the two conditions that you saw in the linear transformation can be combined together to just check for this general conditions. It takes into account also the scalar property, that scalar comes out, and it also takes into account that linear transform 2 vector is sum of the linear transforms. An important example in a linear transform is that let A be any m by n matrix and T be the linear transform going from Rn to Rm, and define this linear transform by matrix times a vector. Okay. So if we define a T, okay, this for the moment may not be linear transform, so may not be linear, right? So we don't know yet. What we are trying to say is that let us take some function and let us define it to be like this, Tx is A times x. Then the question is T linear transform? Okay, so this is again easy to check because let us use the one-step rule. So you're using one-step rule, T of alpha u plus beta v must be equal to T of alpha T of u plus beta T of v. This is what is the check for linear transform. Okay, so is this satisfied here? It turns out that it is satisfied here due to the matrix properties. Okay, so T of alpha u plus beta v is A times alpha u plus beta v. This is alpha au plus beta av. This is alpha of T of u plus beta of T of v. Okay, so this is satisfied. Okay, so hence this implies that T is a linear transform. Okay. So a linear transformation defined by a matrix is called a linear transform defined by a matrix. Okay. Here. Okay, it's called a matrix transformation. Okay. So metric transformations are cool. You may be using this a lot in a variety of areas you may want to work in. For instance, one thing one could do is a shear. Okay, how can I shear a vector? Okay, so consider the matrix transform like this, and it is given by, let us say, this. So what we are considering is T of x is A of x type. Okay. I will show you at the end that any linear transform is actually like this. Okay, so we can prove that any linear transform is nothing but matrix times vector. Okay, so this is a fundamental fact, but we have not proved this yet. What you can assume is that the linear transform is right now defined to be like A times X. Now, let us say that A is this. Okay, so now let us see what it does to the horizontal vector. So this is the horizontal vector, right? So this is my x1. Okay, so the x vector is like is this, right? So y component is 0, right? So x1 0 is, this is the vector I'm considering. I want to know what it will do, what this linear transform will do to all those vectors which lie on the x-axis. So if we multiply that and x1, and if we compute all this, it seems like it did not change the vector at all. Okay, so the vector remains in its own place only. So if I multiply by the matrix on this vector, any vector that is horizontal, it doesn't change the vector. Okay, so it doesn't change the vector. Now let us see what happens to the horizontal vector. Okay, so T is identity, behaves like an identity on the horizontal vector. Now let us see what it does on the vertical vector. Okay, so the vertical vector is like this. Okay, so 0 x2. Now if you multiply it to the vertical vector, we get this, right? So this is like so the vertical vector is pushed perfectly horizontally a distance 3/2 times its length. Okay, so it is moving the vector 3/2 times its length, and it also moves horizontally. Okay, so this is the shearing that I was talking about. Okay, so so the vector, let us say 2 1 here. Okay, so the vector 2 1 here, right? So after the multiplication, okay, so this is moved here. Okay, so I mean 0 1 vector. Okay, let's see like this. So 0 1 vector. So this moved here. Okay, but all the vectors on the horizontal line, they remain fixed. And as you move across this, there is a shearing happening. The moment you have the x2 component, those are being moved like this. Okay, so this is the shearing happening here. So we can also define a linear transform which does the scaling. Okay, so for instance, T of x is x and A is this diagonal matrix. If you choose a diagonal matrix, then it acts like a scaling. Okay, so if I multiply like this, then I only get this thing scaled. Okay, so 2 times the horizontal component and half times the vertical component. So T stretches horizontally. So it's stretched because it's 2 times your vector, and it contracts vertically. So remember the last class I said, if your scalar is between 0 and 1, okay, then it will contract. Okay, so let us say open 1, then it will contract a given vector. It will shorten the length. Yeah, so this is a view of that, how it is along x1, it is stretching, and along y1 it is contracting. Okay, so this matrix is behaving like this. So so you are mapping points of this this initially it's like uniform. Okay, it's a but then for all the points on this, some points here were mapped very far, and the points here came inside. Okay, so so this is how these matrices work. So reflection through a line. So if I choose a matrix to be like this, then it has the effect of reflecting through a line. Okay, so let us say we had some vector here, and if I multiply by this matrix, then it will behave, it will come here. Okay, so it will reflect it through the line. Okay, basically this components flip. Okay, if you flip components, then it acts like a reflection about x equals to y line. Now another important transformation we have is so-called rotation transformation, and this is given by this cos theta minus sin theta cos theta. So this acts as the name suggests, it's a rotation matrix. So given a vector, it rotates anti-clockwise by theta degrees. So if you multiply this to a vector u, then a times u will be the rotated vector. Okay, so we can see the effect of this on 0, 1, 0 and 0, 1. Okay, so let us say this is like 1, 0 vector, and this is like 0, 1 vector. And if we rotate, then we know that it should rotate like this, right? And it should rotate like this. So we know that a theta degree rotation of this, an arbitrary point on this circle is cos theta sin theta. So that is something we actually know. Okay, and this is verified from here. So and this is theta is the parameter here. Actually, if you know the action of the linear transform on these elementary vectors, so these are called the elementary vectors, so 1, 0 and 0, 1. So they form the basis in R2. If you know the action of this on these two, there is enough to know what it will do to the other vector. Okay, so horizontal vector is rotated counterclockwise by an angle theta. Similarly, for the vertical unit vector, which will be this 0, 1. So it will, if you apply on this, it will again rotate it theta degree anti-clockwise. Okay, so suppose T is a matrix linear transform. Suppose A is the matrix of T, then what is T of U? Okay, so so how can you express T of U, right? So what we can do is just do the matrix vector multiplication AU, and the result, if we do a matrix vector multiplication, the result is in RM, and so result will be a vector in Rm. Okay, so that's the answer to the question. Suppose T is a matrix linear transformation. Suppose A is the matrix of T and B is given. So find a vector U so that Tu is equal to B. Okay, Tu is equal to B. So what we are supposed to do, we are supposed to solve the linear system, right? Because T A is the matrix of the linear transform. So in other words, Tx is defined to be Ax. And what you are told is Tu is equal to B, which is essentially Ax equals to B. So we are supposed, or let us say Tu equal to B. So here I will put U. So we can solve and then find the U. So this is another question. So let us say the linear transform is there and the matrix is given to you and B is given to you. So how many solutions are there? Okay. So here, if you look into this example, you can guess actually directly that this is solution may not exist here because of the fact that you have a 0 rows here and it has to be equal to 8. So that will never be possible, right? So even if I plug in x1, x2, x3, then the last equation suggests that 0 must be equal to 8. So this is absurd. So this suggests that this will have no solution at all. Okay, because I can yeah, so I have no possibility to satisfy this. Okay, if there was something here non-zero, then I had some chance that I can choose some x and then make it equal to 8, right? Okay. Describe all the vectors u so that tu is equal to b. So describe all the vectors u so that tu equals to b. This is like asking for all possible solutions. Okay. So one possibility, as I hinted before, is that any linear transform, if we think of, will be a times u is equal to b. So this is like solving for all possible solutions to this this equation, right? Okay. And yeah, so all this should, so here I think something that is missing is linear. Otherwise, all these things won't hold. So this is a review, so I'm going in a plain way, only pointing out important things. Feel free to go through the video, pause and rethink. It's a opportunity to recall things. Okay, so I may not be like very rigorous in these things right now. So which linear transformations are matrix linear transformations? That is, which one comes from the matrices? So this is the answer to my previous question. I said all linear transformations are actually nothing but matrix transform, in the sense that T of u is nothing but A times u. If T happens to be linear, then all linear transforms are nothing but multiplying u with some matrix. So yeah, so the underlying idea, like one can go with the proof of this. The main thing here is that any arbitrary vector x can be written in this form using these basis vectors. Okay, so I can write this like this, and then when I apply the t on this, okay, and then I can observe what is happening to t. So I can write t of x. So what is happening to t, right? So this will be x1 is a scalar, so it will come out due to the property of the linear transformation. This will be t of 1 0 0 0. Similarly, you will have x2 t of 0 1 0 plus xn and t of 0 0 1, right? So I know that I can write this in matrix form, because this is like a you see, this is like a linear combination of the vectors, right? So these vectors are in Rm because t of some vector is going into Rm. So it is now easy for me to see that I can write this in a matrix vector form. So what I will do is that I will stack 1 0 0 vector, and then I will stack t0 1 0 vector, and so on. I keep stacking, and then I collect this x1 x2 xn here. So this is that matrix that you are looking for, A. Okay, so it's very easy, right? So if someone tells you that T is a linear transform, let us say T of xy is defined as x plus y, x minus y, and this is a linear transform. Now if someone asks you if this is a linear transform, then it must be written as A times xy. So what is your A? So the way to find A is like this. You apply T on 1 0 0, okay, 1 0 in this case, since it's R2, and then you apply T on 0 1. You stack those vectors, and that becomes your matrix A. So what I said is being written here. Okay, so I'm not going to do this. Okay, so what I have told you is just explicitly written here. Okay. Suppose T from R2 is a linear transform, so that yeah. So these things are given to you. Then the matrix of the transform is it should be trivial from here. Okay, because so then someone can ask, what is T minus 1 7, right? Well, since this is a linear transformation and the action on these basis vectors are given to me, then it's very easy, because I got the matrix of transform, which is this. Okay, and then I just have to multiply with this guy minus 1 7. Okay, So then from there I get the required answer, right? Yeah. So this is what we did also. Let A be an m by n matrix that has m rows and n columns, and the usual entries will be denoted by Aij or Aij like this. The diagonal entries are those in which I is equal to j, obviously. These are the diagonal entries of the matrix. A square matrix has as many rows as columns. A diagonal matrix is a square and all off diagonal terms are 0. So like this, and all other entries are 0. This is called a diagonal matrix. Upper triangular matrix and lower triangular matrices. So upper triangular matrix is a matrix where only this part, the upper part of the matrix is retained, and below the diagonal everything is set to 0. Similarly, you can think of lower triangular. So everything below the diagonal, like here, is kept as it is in the matrix. So here a star means like this is like A to 1 and so on. So like in the matrix, but everything on the above is made to be 0. So we can add two matrices of the same size entry by entry. Suppose A and B are both m by n matrices, that we can apply entry wise addition. So we can sum matrices like this. A scalar multiplication is also simple. When we multiply a scalar to a matrix, it multiplies to each entries of the matrix. And once we know that, we can do computations like this. So this is scalar multiplication first, here is scalar multiplication, and then we also know how to add the matrices. Okay. Yeah, so we can do matrix multiplications. Remember that matrix multiplication is not commutative. So in general, AB is not equal to BA. Okay, AB is not equal to BA. Especially like if it is rectangular, then obviously it will not be equal, because this way I can multiply, but this way I can't multiply, right? So I cannot think of saying AB is equal to BA or not. Now the question is, what if they were both square matrices? Does it hold that AB is equal to BA? Well, it turns out that it doesn't hold in that case either. So A and B both may be the same dimension, but even then AB here is this, but BA here is this. So they are not equal. So other strange properties that we have is like if AB is equal to AC, then it doesn't follow that B is equal to C. So you cannot cancel out A in matrix equations like this. That is not allowed. That is allowed in the real number, but when you have matrices, it's not allowed. So can multiply. So it may happen that A times B is equal to 0, but still it may not be the case that A is equal to 0 or B is equal to 0. Okay, so these are the things that one should keep in mind. Okay, so here, for example, A is not equal to 0, B is not equal to 0, and B is not equal to 0, but still AB became 0, right? And similarly, we have this example where AB is equal to AC, right? So this is like AB is equal to AC, both are 0, but B is not equal to C. Okay, so B is not equal to C. So this is an example. So these are the properties of the matrices. So it satisfies the associative property. So A times B times C is same as A times B times C. Of course, you are not allowed to swap, right? But otherwise, you can do associative. It distributes left distribution, right distribution, and the scalar can also distribute. So a scalar, if multiplies here, you can first do T times A then B, or you can do A times and then T times B. So applications to the linear transforms, if we want to apply this associative property to the linear transform, remember that matrix multiplication can be seen as a linear transform. So in this case, we are talking about multiplying two matrices, but this is the same thing as saying composing two linear transforms. So T of A of B, T of A of T of B X. Okay, so this is nothing but the function composition, right? Okay, so So the product matrix AB actually can define the function composition. So AB is the matrix of transform of the composition function T of A, TA of TB. And identity matrices are denoted like this. It's a diagonal matrix, but you have ones on the diagonal. Identity matrix satisfies these properties. So any matrix times identity is A from the left side and also from the right side. It doesn't change the matrix. Transpose of a matrix is defined as follows. So any ij entry in the transpose matrix will become a ji entry. Okay. So for example, here is the transpose example. So 2, 0, minus 4, 5. This, if you take a transpose of this, then it becomes this matrix. Transpose, some of the theorems are, if you do transpose 2 times, then you get back the same matrix. Some of the transpose is transpose of the sum is sum of the transpose. And then if you have scalar times A and then transpose, then nothing happens to the scalar. There is no point in doing transpose of the scalar, right? Transpose only makes sense for vectors and matrices. And AB transpose is B transpose A transpose. So remember that there is a ordering has changed here, right? So it's like B transpose first and then A transpose. Yeah, so these are some of the examples here. I'm going to skip this. Then we have something called invertible matrices. So invertible matrices, a matrix is called invertible if there exists a matrix C such that A times C, C times A is identity. There may not be such matrix C, okay, but if it exists, it is the only such matrix. So what this is saying is the inverse is unique. Okay, the inverse of a matrix may not always exist. Okay. Yeah, so uniqueness can be proved like this here. So I'll let you see this. These are simple things. Any seer is invertible. So if you have any matrix that acts like a seer, okay, then it is invertible. So for example, seer matrices look like this, and the inverse can be explicitly computed like this. You just reverse the sign, and that becomes the inverse of this. So any seer matrix is invertible. Another question is like, what is the inverse of this matrix, right? So in the seer matrix was upper triangular, okay? So seer matrix was upper triangular, but this is like lower triangular, right? So this is like another type of seer matrix, but it will contract the horizontal. It will contract the horizontally and stretch vertically. So given the hint that you had before, you can guess what could be the inverse of this matrix. Any rotation is invertible. Okay, so we can explicitly find the inverse like this. Okay, so cos minus sine cos inverse is exactly this. Okay. Okay, elementary matrices I will skip because I have not done this in more detail. We don't need, as I said, like I only need basic stuff. So one of the important things to realize is like if given a matrix is 2 by 2 matrix, and this is invertible if and only if AD minus BC is not equal to 0. And if A is invertible, then the inverse of a 2 by 2 matrix can be found like this. Okay. So we can check explicitly. This is what is being done here. So to check that this is actually the inverse. So and in inverse you put this and in A you put this matrix, and this should come out to be identity. So this can be verified like this here. So you can use this formula. So for 2 by 2 matrices, there is a formula to invert the matrix, and that you can do it. So if we know how to invert a matrix, then we can solve linear systems because X will be just A inverse B. Okay. So we saw that the inverse of this is this, and yeah, so find the solution of these equations. Yeah. So given that the inverse of this matrix is this, now the question is, what is the solution of this? Okay, of this. So this can be written as A times X is equal to B, where A is 1, 2, 3, 4, and X1, X2, and this is 1, 2. Now that you know the inverse of this guy, which is this guy, so you can use the inverse. So X1, X2 is minus 2, 3 by 2, 1 minus half, 1, 2. Okay, suppose A and B are invertible matrices and R, a scalar R is not equal to 0. Then these are the properties you have. So R times A will be, remember this, 1 divided by R, and then A inverse. AB inverse is B inverse A inverse. Remember, order is reversed. B inverse first, then A inverse. Inverse of a transpose is transpose of the inverse. Okay, these are the properties you can check. There is no general way to find inverse of a square matrix. Okay, but we can use those row echelon form that I was describing in the last class. But if you don't remember, you can forget that. So there is a steps. There are steps that you can use to do this. So you can check the slides on these steps. Going to invert this. Okay, so let us see the invertible equations. Okay, so we have seen before that A is invertible if there exists a matrix C such that AC is equals to CA is equal to identity. And identity is indeed this diagonal matrix with all ones. So if A is invertible, then the matrix C is unique. Okay, these things we already know. Okay, now the important theorem on this is the following, that all are equivalent forms. So if A is invertible, it is the same thing as saying that if we do the echelon form, then it has n pivots. Okay, and when put in the reduced echelon form, then A actually should become identity. Okay, so echelon form is like you leave the constants, I mean leave the leading entries, you don't normalize, you don't make it 1. So if it becomes a diagonal matrix with none of the diagonal entry 0, okay, then it's a then it is a it has n pivots, that's what it means, and then it's a invertible matrix. And if you reduce it to reduced echelon form is when leading entries you make it 1. If that is the case, then you have still it's invertible. Okay, so only, okay, if you even skip this, it's fine with me, but the important things to note is this, guys. The only solution to the equation Ax equals to 0 is x equals to 0. Okay, so that's a very important result. If A is invertible, then the only solution to the systems like this will be when x equals to 0. Okay, and for each B in Rn, there is a solution to the equation. So you will always have a solution to the linear system. Because A is invertible, then it's easy now, right? So since A is invertible, x will be A inverse B. So this is the solution to the equation. So this also holds. Like you can also prove this using the fact that it's invertible, right? So there it's saying its only solution is x. So let us assume that there is another solution y, right? So if other solution is also there, and Ax equals to 0 is there, then I will subtract this. So A of y minus x is 0, but A is invertible. So this implies y minus x is A inverse 0. So this is 0. So this implies y is equal to x. So the only solution you can find is x equals 0. So anything else that I started with ultimately became equal to x, which is equal to 0 anyway. So I could not find anything more. And another way in terms of linear transform is like the linear transformation T or A, it doesn't matter now because any linear transform is like A times X. So you can also denote function as A is 1 to 1, okay, or it is onto. Okay, so if that is the case, then either way, yeah, so either way, so the A is invertible, that would force this, or if this is the case, then it will force A is invertible. Okay, so you can try to prove this. Like these are also straightforward, I would say. No big deal. Okay, so 1 onto things you know, right? So 1 onto you know. So from there you can use this to prove that A is invertible. Okay, similarly with onto. Okay, so in a finite dimensional space, actually 1 implies onto and onto implies 1 okay, if A is invertible. Okay, so that's also those results also are valid here. The columns of A are linearly independent. Again, this is like straightforward proof. It comes from here. So if whenever Ax equals to 0 implies x equals to 0, then this is the same thing as saying, let us say the columns of A are A1, A2, An, and x1, x2, xn. So this is like saying the linear combination of x1 a1 plus dot 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 plus xn an. So what this result is saying that whenever this is equal to 0, this forcefully implies that x equal to 0. But this is exactly the definition of linearly independent. Okay, this exactly tells us that columns a1 to ai are linearly independent. Columns of a span Rn. So that is also true because Rn, the maximum number of the vectors, the maximum number of vectors that can generate Rn is n, because anything more than n, remember the result, anything more than n will make it dependent. So if we have the n vectors of A and they are linearly independent, then that is the maximal linearly independent set you found. So it must span whole of Rn. Okay, there is a matrix, there is an n by n matrix C, so that C of A. So yeah, that is actually the definition of invertible. So if A is invertible, then there will exist a matrix C such that, oh, and this is like, we should not have put this here because this is already defined in the invertible case, right? Okay, A transpose is invertible. Okay, so A is invertible, then A transpose is also invertible. Okay. Because we can define the inverse explicitly, right? So because A transpose inverse, I will define is as A minus transpose. So that becomes this, and I know from the previous result that this holds, right? So or I can also write like this: A inverse of transpose. Both are same, and A inverse exists. Okay, so using this, I can prove immediately that A transpose is also invertible. Okay. These are the solutions to this. Now the question is this matrix invertible? So these are the guesses that you have to make. So I leave this up to you. Okay, I mean, you can see clearly, right? There is a dependence. A matrix is invertible when all its columns are linearly independent. This is not the case here, so hence it's not invertible. And these are the things we already like noted down. So I'm not going to do this. So this is still the proof going on for the previous results. So I already gave you the intuitive hint, so I'm not going to do this this now. Okay. So I can skip this. Yeah. So suppose I tell you the equation has only the solution this, then what can you say about this? So this will have a unique solution because if the solution to this is only x equals to 0, then this implies that A is invertible. If A is invertible, then this will have a solution. So I know now that this is invertible. So this is like A inverse this guy, and this will have a like A is invertible, and so this will have a unique solution. So that's what I can conclude. Okay, so then okay. Yeah, and then yeah, so these things were also covered in the previous case, right? If A is invertible, then Ax equals 0, only solution is the trivial solution x equals to 0, and this also implies that the linear transformation is 1-to-1. Okay, so this proof is given here. You can also like these proofs are like if you have done linear algebra, these proofs will be like very straightforward to you. Okay, so like the hint is like you just choose like u minus like yeah. So you, like 1 is like assume that ax equal to au equal to av. Okay. Okay, so this implies so from here you have to prove that u is equal to v, right? So a equal to av you start with, and if you can prove that u is equal to v, then this shows that the linear transform is 1-1. That's the definition of 1-1. So I can do a of u minus v equal to 0, but only solution to equations like this is when this is equal to 0. So u minus v equal to 0. So this immediately gave us u is equal to v. These proofs are very standard, okay, very straightforward. Okay, now let us look into determinants. To any square metric only, you can assign a determinant. Someone asks you determinant of rectangle matrix, then you should not talk to that guy. Okay, so any square matrix only has determinant is defined. Some of the properties of the determinant are as follows. So determinant, if the determinant is not equal to 0, then A is invertible. This is an important result. In the course, sometimes we will use this because depending on the convenience we have, we will sometimes it's easier to prove determinant not equal to 0, then checking explicitly whether columns are independent, or solution to x equals to 0 is always x equals to 0, or the linear transform is 1 1, or the linear transform is onto. So variety of ways are there for invertible check, but very often the very quick check sometimes, if you can find the determinant of A is not equal to 0, then if and only if. So this means if and only if, either way, A is invertible, determinant A not equal to 0, determinant of A not equal to 0, then A is invertible. Determinant of A, B, that's very important result, is determinant of A times determinant of B. Okay, so determinant of the product is product of the determinants. Determinant of identity matrix is always 1. Okay, so yeah, so this is a proof of that determinant of identity matrix. So this we can prove this using using this. So here we wrote determinant of A times determinant of A inverse. Okay, and then this can be written as determinant of A inverse, which is this identity. So this is 1. Yeah, so determinant of actually, yeah. So what we are trying to show here is determinant of A inverse is 1 over determinant of A. Okay, so this is the result we proved using this. Okay, sorry, I mixed this. So determinant of A inverse is 1 over determinant of A, and this is the proof of that. So determinant is really complicated to define actually. So if you recall the determinant formula for 2 by 2, so determinant that we know from high school is like this. So this minus this. Okay, so the A11, A22 minus this. So we can compute determinant. So A is invertible if and only in the 2 by 2 case, AD minus BC is not equal to 0. And the inverse in that case, we know from high school, this is how it is found, and we can explicitly multiply and check that this is indeed the inverse of A. So what happens if we switch 2 rows of a 2 by 2 matrix? So what happens if we switch 2 rows? So let us say we swap these 2 rows and we got the B. So what will happen to the determinant, right? So if you swap once, so these are the properties that you may recall from the previous courses. So in this case, it will be the negative of that. If you swap once, then it's negative. If you swap twice, then it becomes positive, and so on. And there is something called a cofactor of an n by n matrix. So cofactor of an n by n matrix is a submatrix which is n minus 1 by n minus 1 obtained from A by deleting the ith row and jth column. So let us say I want to find the ijth cofactor. Then ijth cofactor will be deleting the jth column and ith row. And the remaining matrix that you get, which is n minus 1 by n minus 1, is a cofactor matrix. So this is what is shown here. The cofactor matrix is like this. So cofactor matrix now, I mean, yeah, this is just like, and then so the cofactor will be defined to be like this, which is determinant of Aij. Okay, so that okay, so that is like an adjoint here. Okay, so far, and then the cofactor will involve the determinant of Aij. Okay, so okay, so the cofactor will be defined like this, and then okay. So yeah, so this is like positive, negative things that I talked about, because this is coming from I plus j. So you will have positive cofactor, there will be negative, and so on. So this is something we know. Okay, so the determinant now can be defined like this. Determinant of A is A11, C11, A12, C12. So I am expanding along the first row, but determinant you can expand along any row, any column. You just have to make sure that the signs of the cofactors are correct. Okay, so determinant of this matrix can be computed. So I believe you can look up into these things. I'm not going to do this now. So this is important. If A is a triangular matrix, then determinant is nothing but the product of the diagonal matrix. So if someone asks you to find a determinant of triangular matrix, remember what was triangular matrix? Triangular matrix is like this is a lower triangular. So everything below is kept and everything above the diagonal is made 0. In those cases, the determinant is nothing but the product of the diagonal entries. So A times D. Similarly, it extends to 3 by 3 matrices. So determinant is nothing but product of the diagonal entries. It holds for both lower or upper triangular. Okay, it doesn't matter. So in general, you can so determinant formula you can use and you can check for yourself that it holds for any. For example, this is a question: what is the determinant of this matrix? So first observation is that this is a low triangular matrix. So determinant is nothing but the product. So product will be like n factorial here. So why does the determinant have great properties? Because determinant is also related to geometry actually. So if you take the determinant of two vectors, so let us say this vector is this one, and let us say this vector is v, and let us say this vector is u, and the components of the vector are v1, v2, and the components of this vector are u1 and u2. Then if you compute the determinant, then it gives you the area. Okay, it gives you the area of between this rhombus. Okay, so it calculates the area of this. So this is what is it's shown here, and the same thing will happen. Yeah. So yeah. So when you are doing transformations, then the determinant acts like a scaling factor, okay, of the area. So for example, if I'm multiplying this, if I am transforming this by a matrix A, okay, so I'm doing a linear transform of a square by a matrix A, then how the shape will be of the transformed image depends on the determinant. Okay, so if the area was some C, then the area after the transform will be a scalar multiple of the determinant. So it will be determinant times the C. Okay, so this is what happens in general case. Okay, so for instance, this face is being transformed using a linear transform, and this becomes this face. So the area change that you see, that will be the determinant of the matrix of the transform. Okay, determinant of the matrix of the transform. Okay, so yeah, so like the determinant can be negative also, but it just means that the figure became flipped. Okay, so that's why since you are talking about how much factor my area reduced, you take a mod of the determinant, so that because area factor reduction in the area it should be a positive factor, right? Okay. Same thing can be extended to the volume of a parallelepiped. So volume of a parallelepiped indicated by these three vectors is nothing but the determinant of this. So so in general, if n is large, then calculating determinant is not so easy task. Okay. Okay. So what are the properties of the determinant? We have seen properties of the determinant. So this represents a change in the area or volume. Determinant of AB is determinant of A, determinant of B. Determinant of A, if it becomes 0, then A is not invertible. Determinant of identity matrix is 1. Okay, so and the definition is complicated, but one can define define determinant to be like this. So expansion linear combination of the cofactor. And yeah, this thing is already like yeah. So determinant, what is the role of what happens to the determinant if you have scalar multiple of the vector, right? So what can I take out the scalar, and so let us say in this case 3 is common. So I can take out 3 common. Okay, and then I can keep the other things inside. So yeah, so you can expand this in variety of ways. So if you multiply a row by a scalar, then the determinant will be multiplied by the same scalar. So this is what is being proved here. Suppose a and b are n by n and b is 5a, then what is determinant of b? So determinant of b will be determinant of 5 of a, but 5 is a scalar that comes out. So it will be 5 of determinant of a, right? Yeah, is it 5 only times the determinant, or is it like more than that? Because here, if you see, it's a row is multiplied by 5, right? So just for a row factor, if you bring out, you got like just okay here, right? So just one row, let's say the ith row is multiplied by 5, then you have 5 times determinant. So what will happen if you have all the rows of a multiplied by 5? Okay, so you have to be a bit careful here. So what if all the rows are multiplied? So you try to see what could be the correct answer here. Okay, just one row brings one factor out, right? So there are n rows now. Okay. Okay. So if you swap, then we have already seen if we swap two rows, then the determinant changes the sign. Okay, I will skip these things. Yeah, so these are the results on determinants. Yeah, these are again the results going on the determinants. Yeah, how can you use these rules? Yeah, so you can use some of the rules to compute the determinants here. Yeah, I mean, you can do some row subtraction and so on, and those type of row operation don't change the determinant, and then you can make it into a little bit of a simpler matrix. And then once you have that, then it is better to expand along this so that you have a very simple determinant to compute at the end. So you are legally allowed to do some subtract some rows and take out factor of the rows and so on. In general, to compute, you can start with you can reduce a to actually a row echelon form, and the determinant will be product of the diagonal entries at the end. Okay, so you can do this, see this example, and these are detailed. So you can do row exchange, whatever is needed, and you transform this into a nice upper triangular form. Okay, and then from there you can get the determinants. And since each time you are doing some row operation, let us say row swapping or whatever, so for that you have these factors coming out, and then at the end you can compute the determinant. And yeah, so there are concepts of vector spaces. So in if you think of functions, then we can add functions like this. So that's how the function addition is defined, and we can multiply a function by a scalar and so on. Yeah, this is just a function evaluation here, and set of all polynomials of degree at most n. Okay, so you know this, how to multiply this and so on, how to do scalar multiplication and so on. So I will skip this. I'll skip this. Yeah, so there is something called vector space. So vector space, we can define a vector space to be a space where for any arbitrary x and y, addition is defined and scalar multiplication is defined. So a simple vector space example could be Rn. So you can take any two n-dimensional vector, and I know how to add the vector, and I can also do scalar times the vector. So, and further properties, so this is a property of the vector space itself, and they are commutative over addition because addition is commutative. So they are distributive. There is an element 0 such that x times 0 is 0 times x and so on. And similarly, I can, so for each vector x, there is also a negative of that vector. Okay. So these are some of the more elementary properties. So this is another question here. So consider all the polynomials of the form this. So is this a vector space or not? So that's the quiz that you may try to answer. What are the consequences of a vector space? In a vector space, 0 times a vector is supposed to be 0. -1 times a vector is the negative of the vector. And scalar times a 0 vector is a 0 vector. So this is the thing I have already described before, the parallelogram law and all this. Okay. Yeah, so there is a concept of a subspace also. So subspace is nothing but you take a set which is a subset of a vector space, and as a subset itself, it satisfies these three properties. 0 is there for x and y in U, x plus y is there, and for any scalar multiple in R, scalar times the vector is in U. Okay. So any subspace of a vector space is a vector space in itself, obviously, because the way it is defined as a standalone, it's a vector space. Okay, so here there is another question. I leave it up to you. So these are some important subspaces that we are interested in. So let A be an m by n matrix. Then consider a set of all U such that Ax equals to 0. So what we are trying to define is a null space. So null space is sometimes also written like this. So this is the collection of all vector x such that Ax is equal to 0. Okay. So find out all possible vectors such that Ax equals 0, and that becomes a subspace. Okay, that becomes a subspace of Rn. Is a subspace of Rn. Okay, so and you can prove this. Okay, you can prove this result that this is that 0 is there. If U and V is in the null space, then U plus V is in the null space. If scalar times a vector in null space is also a vector in the null space. So all these things you can prove. The proof is already there. Yeah, so there are some examples which are not a subspace. So you can consider this. So for example, if you take R2, so R2 is a vector space. But if you consider only this part, okay, where x is greater than equal to 0 and y is greater than equal to 0, okay, then this will not form a vector space. Okay, so then this will not form a vector space. So so this is the proof for that. And the proof follows from the fact that although 1 1 is in the subspace, so for example this is there 1 1, but if I take a negative, because since you are only considering this, but negative will be -1 -1, but this is not there. Okay, for this to be a subspace, any scalar multiple should have been here itself. Okay, but this is not the case. Okay, there is another non-example, so I leave it up to you to go through this. So we already know about the span. So span. So we can take a vector this, and we can make a span of that, and span itself will form a vector space. Okay, so you can take a span of these guys, and this will form a vector space, right? So space of a third degree polynomials, right? So you can generate all third degree polynomials using this. So span is, that's what I said, span is always a subspace of a vector space. So 3 criteria could be satisfied. You can check this criteria. Okay, so I have to stop here, and remaining part of the review we can continue with the optimization method from the next class, and the remaining part of this review of the vector of linear algebra will be done by the TAs with these slides. They will run you through the linear algebra part. There won't be any question from linear algebra in exams for tau or anything, but it is important that you know